Okay? Polynomials. First thing we want to talk about, again, the rules of exponents. So our exponent rules when we're dealing with variables and bases, okay? So the rules of exponents, and this is not necessarily order of operations type things. This is like combining things together. So we'll start with the product rule. The product rule in math, the word product means multiplication. So it's a multiplication problem where you have a base with an exponent times something with the same base and an exponent. The rule is, if the base is the same and they're multiplying, you do what with the exponents? Does anybody remember? You add them. Yeah, m plus n. Okay. And what I'm going to try to do here is I'm going to put the generic notation there on the left, and on the right side of that line, I'm going to put a real example. Okay, so that might be like x to the fifth times x to the third ends up being x to the 5 plus 3, which is 8. Okay, so there's the generic rule and then an example beside it. That's what I'm going to try to do there with these so that we get those things going. Okay, so there's our product rule. The power rule is where we have a power, a base with an exponent, and that's inside parentheses with an exponent outside those parentheses. So we have something with an exponent raised to an exponent. The rule is that you multiply those exponents. Example might be x to the 6th power squared. That would be x to the 12th. 2 times 6, 12. Parentheses, exponent on the outside, says you multiply those exponents together. That is the power rule. Power rule, part 1. Kind of a subset of that power rule. What if you have more than one thing inside of the parentheses? So here, this first one, we just had the a to the m power inside of there. If you've got something else, let's say you had a to the m, b to the n, and that's inside parentheses. Those bases are not the same, so you couldn't put those together. But then we have an exponent outside here, and let's call that the x exponent. The rule is that those things would all get the exponent multiplied to their exponents. It's like distributive property. Remember what distributive property means? Multiply to everything. So x times m, x times n. So that would be a to the mx times b to the nx. An example of that might be that you have x to the 3rd, y to the 4th, in parentheses to the 5th power. So that would be x to the 3 times 5, which is 15. So we have x to the 15th, y to the 4 times 5, 20. We get that rule. Okay, so if there's more than one thing multiplied together inside of the parentheses, you're going to put that exponent multiplied to both things on the inside. Both exponents on the inside. Another part of the power rule is if you got a fraction. Got different bases. Got an A base with an M exponent, a B base with an N exponent, and then some other exponent on the outside of the parentheses. Okay, so that's very similar to the previous rule. It just multiplies to both of the exponents. You might have x to the third, y to the seventh, all that raised to the second power. It'll be x to the sixth, y to the 14th. That's what that simplifies to be. Okay. So that power rule really has to do with the parentheses with an exponent on the outside. That's what makes you know it's a power rule, is the parentheses with the exponent on the outside. Okay? All right, one more rule. Quotient. We won't use this one a whole lot in this section, but we're talking about exponent rules. Let's go ahead and get the quotient rule. Quotient rule deals with the same base. Maybe we got m on top, a to the n on bottom. When you were multiplying the same bases, you did what with the exponents? The product rule was we added, right? Well, the opposite of multiplication is division. So the opposite of addition would be subtraction. So I'm going to subtract those two exponents, a to the m, top minus bottom. We had x to the 13th over x to the 5th. Subtract those would be x to the 8th power. So examples of each of those rules there beside them. Again, I'm not going to use the quotient rule too much in this section, but I did just want to go ahead and talk about it since we're talking about exponent rules. Okay?
So, am I going to write product rule and put multiplication, and then power rule, addition, and then quotient rule, subtraction, or will I be messed up later?
Well, just know that the product rule you're going to add. So product, you could write add there. The power rule, you can write multiply. Yeah, that would definitely be helpful in knowing that. And the quotient rule, I'd subtract. That's definitely can help you remember those rules as you go along there. Okay. All right. Let's do a few examples here of various kinds. Get up a little bit so we can put these rules into action. So the instructions would say simplify, and then we might have, call it example A, y to the 6th times y to the 5th. They're multiplying, so what are we going to do with the exponents? Add, because the bases are the same. The base is y on both of them, so that means we can add those exponents and get y to the 11. 6 plus 5, okay? And we can go example B just here beside that. What if they throw numbers involved there? So maybe they got 3x to the 3rd times 4x to the 5th. What do we do with those numbers that are in front? Yeah, it's just a multiplication problem, so I'm just going to multiply 3 times 4 and get 12. And then what's the rule for the x's? Add them up. So 3 plus 5 is 8. 12x to the 8th. Okay. Example C. Let's make it very difficult. Level expert. 3 of them. Maybe it's not level expert, but it's a little more difficult. So, what happens to the numbers? Multiply them together. So we got 6 times 9 times 2. I don't know my...
108.
Be 108? Yeah, I don't know my 54 times tables, but I do know my 2's. So it's 108 x to the 10. Yeah. 5 plus 3 is 8 plus 2 is 10. Okay? Example D, x to the 5th squared. Very similar to one of them we just did. Parentheses with an exponent outside. So what's that going to tell us? What do we do with our exponents? Multiply. Parentheses tells us to multiply them. So that's going to be x to the 10. Not too bad. E. What if we had 2 to the third power on the inside? So that's just a number with an exponent, nothing bigger. You know, no big deal. And then x to the fourth power inside there as well with parentheses. And then let's put an exponent on the outside. Let's use a 3. So there's more than one thing on the inside of the parentheses. Okay. But there's parentheses with the exponent outside. So that tells us to do what with the exponents? Multiply. Which ones get multiplied by 3? Both of them. Even though that's an exponent on a number, it ends up being 2 to the 9th power and x to the 4th power, or 4 times 3 be 12, right? Now, 2 to the 9th power is a number, right? We could work that out if we needed to. So we could do, with our calculator, we could throw 2 raised to the 9th. 512. So we could write that as or 512 x to the 12th. Because it is a number raised to a power. Know that it's both of those. Don't necessarily just always rely on working out that number, but understand that 2 to the 9th is 512. Yes, sir?
So where are you getting the 512 out?
2 to the 9th power.
So you multiply the 2.
I did 2 times 2 times 2 times 2 times 2 times 2, 9 times. And that's working it out with the calculator there. When it's a number to a power, you can work that out. If it's a variable to a power, you don't know what the variable is, so you just leave it.
So you just have to either or?
I want you to know that it could be either or. Because sometimes you're going to, if that number's not real big, like 512 is not that big a number, but 2 to the 50th power, really large number. So, you probably wouldn't work that one out. So just understand the exponent rule part of it, that it could be written as 2 to the 9th power, or it could be written as 512. Okay? Yes, sir? Yeah.
See, I thought you would multiply maybe like 3 by 2. Multiply everything within the parentheses.
Well, that's an exponent of a 3, so that's 2 to the third power, which, if you did that, would be 8 x to the 4th to the third power, which, if that would be 8 to the third x to the 4th, which equals 512 x to the 12th power, sorry. That it works the same way if you did work that out, following order of operations by doing that 2 to the third power on the inside. 2 to the third power is 8. And if you cube 8, that's 512 as well. It's the same number. You're going to get the same final answer there. Now, as far as whether, they're probably not going to do it that way. They're going to leave it 2 with a base because it's a smaller number. You get a better exponential representation of that because 8's a composite number. Normally, if you're going to write it in exponential form, you're dealing with prime numbers at the bottom as the base. 8's not a prime number, but 2 is, because nothing else goes into 2 but 2 and 1, right? So that's a prime number. So they're going to usually, if they're going to write it in exponential form, they're going to leave it as a prime number as the base. So that's why I left the 2 there, because it's a prime number instead of working it out. But very good question, because order of operations would say do 2 to the third power first out of that. But you end up with the same answers there. All right. See if we can get another one here. Very similar problem. You got 3 to the 5th power over n to the third power. Put that in parentheses to the 4th power. So I could see, order of operations saying do 3 to the 5th power first and get that number, 3 to the 5th power. It's going to be, 243. It's not a huge number, but it's a number that's bigger than 3, right? But we're ending up going to have to take 243 and put it to the 4th power. Or we could do the exponent rule here and get 3 to the 20th power over n to the 12th power, 3 to the 20th looks a lot like it's going to be a lot bigger than 243, right? 3 raised to the 20th. Really, really large number. If you did 243 raised to the 4th power, same really large number, no matter which one you do that. Now, so for this one, I definitely could see them not working out that number and just stopping there and saying it's 3 to the 20th over n to the 12th. Don't work out 3 to the 20th because it's that big long number. 3. Oh, let's see. There's million. There's billion. 3,486,784,401. It's a large number. Not quite the national debt, but it's big. Okay, so I could see them leaving it as 3 to the 20th, and they would leave it write it as 3 to the 20th, and not 243 to the 4th, because 3 is a prime number, and 243 is not. So that's the difference in how you'd want to do that. We tend to try to apply all the exponent rules before we work out the number parts on these problems, just based on, and I will be very clear on test, write it in exponential form or work out the number, that sort of thing. I mean, and if it's multiple choice, it'll be clear which one you want to do because it won't have both on there. Okay, it'll be exponential form with 3 to the 20th, or it'll be 3,486,784,401. So it very likely it's going to be 3 to the 20th. Exponential form is usually more common than the worked out number, unless it's like 2 squared, and that's too easy to not work out. So, all right, let's look at another one. See if we can kind of clear this up a little bit. Example G. Let's say we had -2, then an m to the 6th power over x squared, and then a y. Let's put that all in parentheses to the 5th power. Yeah. That's a lot, man. He's got all kinds of stuff in there. Eat your Wheaties before you do this one. All right, so the key thing here is you look at it and you say, okay, well, the -2 on the inside, does it even have an exponent? Is there one written there? No. Would he even be talking about it if it didn't have an exponent, though? It's got a 1 exponent. It's understood to be a 1 exponent. So what I usually do is I go back in there and put those 1s. On the parts that don't have exponents written, I go in there and throw 1s on those. So it helps you remember, you got to multiply those by the exponent on the outside as well. If you don't, you're missing something. Okay? So -2 raised to the 5th power now. M raised to the 5 times 6 is 30. X raised to the 10th. Y raised to the 5th. And you could leave it like that. Or if they worked out the -2 to the 5th, that's not really that big a number. It'd be -32. M to the 30. X to the 10. Y to the 5th. Again, the box end one, that's going to be the most common one you're going to see. But since -2 raised to the 5th is not a really large number, working it out is not unheard of. But it's more common to see it written in exponential form, especially in this section. Okay. All right. One quick definition type thing is the 0 power or the 0 exponent. It's the easiest one in the world. Maybe next to the 1 exponent. It's really easy. Anything to the 0 power is equal to 1. No matter what the anything is. I could take that crazy number, 3,846,784,401, and if I raise that to the 0 power, it turns into a 1. Always. By definition, anything to the 0 power is 1 by rule. Anything to the 0 power is 1. We could take a glass of water, or maybe whatever else you want to call this. Glass of water, raised to the 0 power, 1. No matter what you raise to the 0 power, it's 1. Get that going in your brain. And understand, anything to the 0 power is 1. No matter what it is. Okay? Alright. That will allow us to skip several problems. Let's go to this example, though, because it really is important to do this one. What if you had a negative sign and then a parentheses and a -4 on the inside, and then that raised to the 0 power? What's 1? What part of that's 1? The whole thing or just part of it? The part that the parentheses is with. Yeah, so this part turns into 1, but then what's that negative out in the front do? It stays there. So that makes that what kind of 1 over here? A -1. That's the most problematic type of problem with the 0 exponent, is when that negative is hanging out in the front. It has nothing to do with that 0 exponent. The -4 in the parentheses had the 0 exponent. This negative out here is kind of like, okay, it says -1 times -4 to the 0 power is what that means. Okay, that's kind of what it's saying there. So like maybe if you had a variable there, maybe you had a negative and then you put x to the 3rd to the 0 power like that. What you want to think about is, oh, that's -1 times that other, the next part. That's the key to that problem, is that -1 in front. And that would be -1. This part turns into 1, right? Because anything to the 0 power is 1. And then -1 times 1 is -1. And that's what that turns into. Okay, so that negative hanging in the front is where some mistakes can happen. You got to be careful there. Yes, sir.
So you still got 0, but you got to be certain that the negative is 1.
You got the 0 power, turns it into 1, and then the negative in front makes it a -1. Is what happens there. That the 0 power turns whatever's inside of the parentheses to 1, and then the negative out in front makes that a -1. Yes, sir.
You do an equation where I could see where it could get confusing, like in a certain equation. Can you do that?
Yeah.
Like,
what I'm trying to say?
I think I could do.
Or it'd be tricky. It'd be almost like
But kind of,
It could throw you off.
it could throw you off. Yeah. Let's see. I'm trying to think of something that's well, maybe you had this 2x squared y to the 5th over w to the 3rd to the 0 power times, maybe you got x to the 5th y to the 2nd over w to the 0 power, and then the -1 here. So a lot going on there, but what do you know about this part? It's 1. A lot of stuff in there. Doesn't matter what it is, though, because it's got a 0 power. It turns into a 1. Okay, so we got 1. What do we know about this part? It's 1. And then we got the -1 that was there to begin with. So we're multiplying all three of those together and getting the -1. The only difference in that and the previous problems is where the negative is at. That's the same problem if I put the negative right here in the front. It's the exact same problem. It just gets missed because you forget about that negative being right there in the front. And they don't put the 1 there. Is that kind of what you're
Yeah,
asking for?
similar, but more of like just take like the division problem out and say you got like 2x squared minus, and then I guess y to the fifth. Put that in parentheses to the 0 power.
Like that?
Yeah, but minus that. Like 2x squared minus y.
Oh, well, that's a whole different game, but...
You know what I'm saying? Like that.
Well, I mean, if you go to simplify that, I mean, it's going to be
Or that just...
minus 1.
Okay.
And then that's it. There's really
Okay.
not much you can do there as far as getting that to do anything else. Just evaluate the exponent part. The 0 power turns into a 1. And then the other part didn't have anything to do. There's no work to be done on that part. Most of what all you're going to see for these particular parts of it is the idea of simplifying and following those rules, the power rule, the product rule, the quotient rule type things. Out of that. Again, not quotient rule very much in this section. We'll get to that later, I promise. Okay. All right, so there's our rules with exponents on simple pieces. Let's talk about kind of this leading, example K kind of leads into the next part of this section, which is taking polynomials and actually starting to do some stuff with them, look at the properties of them, and maybe talk about simplifying them a little bit, adding, subtracting some polynomials, which is a little bit more like this. There's probably not going to be as much evaluation of exponents involved in that, but there might be some that comes up.
What if,
Brian?
like, say, like on example K, you had a negative, or take y out and put it as a regular number there, but it's negative.
It's still to the 0. It's still anything to the 0 power
So it's
is
still
1. Still turns into a 1, even if it's a negative number inside. That's always going to, no matter what's inside, if it's to the 0 power, it turns into just a regular 1. And then the minus sign on the outside makes it minus 1.
So if it was the negative sign in front, like where the 2x is at, so before that it would turn it negative, right?
So like that, and then maybe you got a negative 6 to the 0 power like there. So there you're going to get negative 2x squared. Nothing changes about it. But then this part turns into 1. It's just minus 1. But nothing, it doesn't matter what's inside of there, whether it's positive or negative number. The 0 power trumps it all and says, it's a negative. Or it's a negative, doesn't matter. It's a 1 now. Because I'm a 0 power, and that's what I do. Turn everything to 1s. Okay. All right. Let's look at polynomials. A few little quick definitions here just to get us back thinking about polynomials from maybe a high school algebra class from way back, or maybe not as far way back. I don't know. Let's look at polynomials. Polynomials just means terms added or subtracted. Okay? What are terms? Terms are the pieces. Separated by addition or subtraction. Okay? There's these parts of these polynomials called the coefficients. Coefficients just means numbers in front of variables. Okay, those are the coefficients. Degree of a term. Degree is kind of like a property of a polynomial. So if we're talking about the degree of a term, that deals with the sum of the exponents. So this is where this relates to what we're talking about earlier, the exponent stuff. So the sum of the exponents on the variables only. Okay. So when we look at a polynomial, I don't know what letter we're on now. M for this section. If we want to state the degree of the polynomial, so we're going to learn how to do that here. Really an easy thing, not a whole lot of math involved. State the degree of the polynomial. So you've got a polynomial, 2x squared plus 5xy to the third minus 6x. What you've got to look at are the exponents on the variables only for each term. Okay? So we need to find the degree of each term. Okay? The first piece only has one variable, the first term. 2x squared is a term. The coefficient is the 2 in the front. The exponent is on the variable, it's on the x. So the degree of the first term, so I'm going to write term degree here. The first term, its degree is 2. The degree of the second term, there's two variables, right? There's an x. What's the exponent on that x? It's a 1. And there's a y to the third. The degree of that term is the sum of those exponents. 3 plus 1 would be 4. And then the last term has an x. What's the exponent on that x? It's a 1. So the degree of that term is 1. Okay? So you get the degree of each individual term, and then to find the degree of the polynomial, it's the biggest one. That's all it is. It's the biggest one. The degree of the polynomial is the largest term degree. So 4. So the degree is 4. Finding the degree of a polynomial. Get the degree of each term and then pick the biggest one. Okay? When there's more than one variable, that's when you got to do a little bit of math, but there's not a whole lot of math involved in there. It's just adding 3 and 1, that's 4. That sort of thing. So if we look at this example, we want to find the degree of this polynomial. Let's say it has 4x to the third minus 5x squared plus 6x to the fifth minus 7. This one's even easier, because if I look at the degree of each term, what's the degree of the first term? 3. There's only one variable to look at, and I only look at the exponent on that variable. The exponent on the x is a 3. What's the degree of the second term? 2. It's the exponent on the variable. What's the degree of the third term? 5. What's the degree of the last term? Is there a variable there? No. So if it's not there in math, nothing in math would be 0. The degree of that term is 0. Then pick the biggest. What's the biggest? 5. Degree is 5. That's what we want. The coefficients don't matter. The numbers in front don't matter when we're talking about degree. They matter if we're talking about simplifying a problem. They don't matter if we're talking about degree. The coefficients are not part of the degree. The exponents on the variables only are part of the degree. Let's look at another example of that. Say we had something with 2 variables in it, so it's a little bit more college level, I guess, maybe. What's the degree of the first term? 7. 4 plus 3, 7. The degree of the second term? 6. 5 plus 1. There's a 1 on that y, so that's where the 6 comes from. The degree of the third term? 8. 6 plus 2 is 8. The degree of the whole polynomial, the biggest one, 8.
So if you had 3 layers, you add all 3 of them together?
Yes, if they're on the same term, yes. Yeah, absolutely. Ever how many, it's only the exponents on the variables. They have to be, like each term is separated by addition or subtraction. So you separate it and look at each individual term and add up the exponents on those pieces. Absolutely. Okay? So degree, that's going to help us later on when we go to start solving polynomials later on in the course. If we know the degree of the polynomial, it's going to help us know how many answers we should end up with. So that's one of the reasons that we start talking about it now, to talk about the degree, because when we start talking about some of the things as we go forward, we get to first degree problems, they have 1 answer. We get to second degree problems, they have 2 answers, because second's the degree of 2, right? Okay, so that's where we start talking about that now. So let's talk about, with polynomials, we can name them. Name a polynomial. I named my polynomials Davis and Jonah. No, that's my kids. Polynomials can be named by how many terms they have. Okay? Polynomials can be named by how many terms they have. So, little chart here. Number of terms. Terms are separated by what again? What were terms separated by when we were talking about degree? Adding and subtracting. That's what separates them. So when we count terms, we're counting how many pieces are separated by addition and subtraction. So, and then we'll do an example. So number of terms, the name that it goes by, and how many, an example of that. So if there's 1 term, the prefix that means 1 is MONO. And it's called a monomial. Monomial. M-O-N-O, mono. I'm a sound tech too, so when you're running a mono signal, it's just one side of the headphones, not both. So monomial, 1 term. An example of a monomial could be something just like 2x. There's no plus or minus of anything else. It only has 1 term. It's one piece. What would the degree of that piece be? 1. Yeah, the exponent on the x is a 1. So the degree of that polynomial, that monomial in our case here, because it's only 1 term, is 1. Okay? All right, so if it's got 2 terms, what would be the prefix for 2? Binomial. A bicycle has 2 tires. A binomial has 2 terms. Separated by addition or subtraction, so x squared minus 9 would be a good example of a binomial. What's the degree of that binomial? 2. Exponent on the variables, 2. So the degree of the first term is 2. The degree of the second term is 0, so the degree is 2, the biggest one. Okay. 3 terms, trinomial, like a tricycle, or a triathlon. And good example of that, it's one of my favorite ones, x squared plus 7x plus 12. It's got 3 terms, 3 pieces that are separated by addition or subtraction signs. Okay. Now, anything with 4 or more, we don't try to find that prefix for. So we wouldn't do a quadrinomial or a quintuple, or it's hard, you can't even say it. So anything 4 terms or bigger, we just call it a polynomial. Poly means what? A lot. Many. Polynomial means many. So polynomial, example of that, might be something like x to the 3rd plus 5x squared minus 6x plus 36. Something like that. That's a polynomial. It's got 4 terms in it. But anything bigger than 3, we call it a polynomial. We only name 1, 2, and 3 term polynomials. That's monomials, binomials, and trinomials, respectively. Okay, so when we start talking about those, that's what we want to do. Okay? All right, let's talk about adding and subtracting polynomials, and then classify what kind of polynomial we got after we're finished with that. so we can combine two birds with one stone kind of idea here with this last part of this section. So simplify. Very much the same thing as what we did in the last section, but with polynomials here that are a little bit bigger. I have no idea what letter we're on. P. All right. So here's a polynomial: 2y to the fourth minus 3y to the second plus y. And then we're going to add that to another polynomial. So that's a trinomial. I'm adding it to, it doesn't have to be a trinomial. It happens to be in this one, but it doesn't have to be. 4y to the fourth, 7, excuse me, y squared. And then let's do a minus 6y. Okay. So what we look for, if we're going to simplify, are like terms. What does it take to be a like term? Same variable, same exponent. It has to be both. Okay, so that means 2y to the fourth has what that's a like term with it? Yeah, 4y to the fourth. And when I add those two together, do the exponents change? No. Remember our exponents rules, we didn't have one that was a sum rule. We had one that was a product rule that said multiply, but we didn't have one that was an addition or subtraction rule. So the exponents don't change. Only the coefficients change. So we have 2 plus 4. So 2 plus 4 would be 6 y to the fourth. And then we put our y squareds together. Negative 3 plus 7 be positive 4 y squared. And then we have a positive 1y and a negative 6y. Negative 5y. What would we call that? What name would it have? Trinomial. It's got 3 terms, so it's a trinomial at the end, after we've simplified it. Okay, so you want to simplify before you classify. All right. Parentheses, negative 8m to the second minus 3m to the third plus 4. Close those parentheses. So there's our first little trinomial. Minus, let's do negative 3 plus 7m squared plus m to the third. So another trinomial that we're adding to that, or subtracting from that. Excuse me. They're the same thing. So what's the difference in this? Is there a difference? They're not in the same order, but does that matter? No. I tend to do this, kind of in order, just because I like to do things in order. So I always start with the highest exponent first, just to go ahead and get it out of the way. Is the thing that's got the most power, the biggest exponent, right? So what goes with the negative 3m to the third? All right, so what operation's combining those? Subtraction. So negative 3m to the third minus 1m to the third. Negative 4m to the third. So be careful on your minus sign. Okay? And then the next thing, I got 2 things that have an m squared, so I'm going to put those together. Negative 8 minus 7, negative 15 m squared. And then I have a positive 4 minus a negative 3. This is the one that usually gets people. Plus 7 minus 7. Plus 7. Good job. Double negative makes a positive. The minus a negative. And then that would be classified as a what? What is this? Trinomial. Got 3 terms. What's a trinomial? Not too bad. Not too bad. A couple more in this section, and then we'll get the last one. All right, so 8m to the fourth, p to the fifth, minus 9m m to the third p to the fifth plus 11 m to the fourth p to the third plus 15 m to the third p to the fifth, and then let's get one more piece, plus 6 m to the second Ugh. Is it okay that not everything matches up? Is there something that matches up? Where? Okay. Okay, yeah, those two match up together because they have the same variables and the same exponent on those variables. So that makes them like terms. So we can put those two together. So negative 9 plus 15 would be six m to the third p to the fifth. So that takes care of those pieces. So I'm just going to splash those out. Is there anything else that goes together as like terms? No, even though the 8m to the fourth p to the fifth and the 11 m to the fourth, that's not p to the fifth, that's p to the third. So they're not like terms because they have one piece that's different on the variable and exponents. It has to be matching perfectly for those to be like terms. So we're just going to copy down the rest of it. That's a positive 8. So I'm going to put plus 8m to the fourth p to the fifth. That's a positive 11 m to the fourth p to the third. And then that's a positive 6m squared p. Big ugly thing that we would classify as a what? Polynomial, because it's got more than 3 terms. Good job. Polynomial. Okay? So adding, subtracting polynomials. Let's do the hardest one that we've done so far. You may not think it's very hard. I don't know. All right. 4 parentheses x squared minus 3x plus 7. And then we have a minus 5 parentheses 2x squared minus 8x minus 4. Good times. All right. What do we need to do with that?
You'd subtract your x2 and 2x.
Can I do that yet?
Well, you have to work 45. You'd subtract those first.
Can I? Why would I distribute first? Absolutely. Order of operations says multiplication comes before addition or subtraction. So that's why we've got to do distributive property first. Okay? Not because our 8th grade math teacher told us we had to. It's order of operations is the reason they told you that. So distributive property, if you see that in the problem, you're supposed to be simplifying. We always do that first. And go ahead and get that out of the way. The reason we get it out of the way first is because it's order of operations. And multiplication comes before that. So I'm going to distribute a 4 to all 3 of those terms. And when I distribute, what operation am I doing? I'm multiplying. So that's 4x squared minus 12x plus 28. And then when I distribute this 5, I'm distributing a minus 5. Be careful of that. That's a very common mistake, is to distribute the 5 and not the negative with it. And that can cause you some sign mistakes as you go. So distribute negative 5 to all 3 terms. That'd be a minus 10x squared. That turns it into a plus 40x and then a plus 20. So if you did not distribute the negative sign, you could very, very easily miss the signs. And you'd still have like terms, but it just wouldn't come together to be the right amount of like terms. Okay? Now let's put the like terms together. So we got 4x squared goes with negative 10. So that'd be negative 6, right? And then Those are done, so maybe I'll slash those out because I'm done. And then 12x negative plus 40x would be 28x positive. 40 minus 12. And then those are done. So then 28 plus 20. 48. So we ended up with a what? Trinomial. We could classify that as a trinomial. We needed to. Not too bad. Not too bad. Okay? All right. So, our section R3.